Hi, my name's Brad. I'm an applications engineer with Keithley Instruments and Tektronix. In this short video, I'm going to be showing you some interesting applications of a Keithley Source Measure Unit, including simulating electrical brownouts and dropouts. Along the way, I'll be showing you how to configure sweeps and pulse trains with a Keithley 2461 SMU. We'll be viewing the results of these dropouts and brownouts with the Tektronix 5 Series mixed signal oscilloscope. For a device, we're using the 5 Series' demo board. Let's get started.
Here's a diagram of the setup we'll be using first to simulate a dropout. We'll be connecting to the frequent anomaly signal on the demo board with our 5 Series MSO. This signal, as you may guess, usually shows a basic pulse signal, but every now and then has an anomaly show up. We're powering the board with a 2400 series graphical source measure unit, in this case a 2461. For a connection, we're using a USB Type-B cable that's been modified to have safety banana plugs on the other end. To look at the brownout behavior, we could simply set the voltage level, but sometimes more interesting is looking at how the device behaves as it approaches the brownout level, so we're going to configure the SMU to perform a sweep. We want to look at how our device enters and recovers from a brownout state, so we're setting up a dual linear sweep to sweep from 5 volts, the normal operating level, and 3.2 volts, just about the brownout level. We're going to define this sweep based on the number of points, rather than specifying a voltage level difference between points. 50 of them should be fine. We'll set the sweep to repeat twice for now. I know the first sweep will show the turn-on behavior of the board, which we're not interested in right now. Then we'll set the current limit to 900 milliamps. The board normally operates at 800 milliamps, so we'll set the limit a little higher to capture interesting behavior without damaging the board. Next, we press Generate to create the sweep and load it into the SMU's trigger model, and finally press Trigger to start the sweep. You can see the SMU's output light turned on. Let's head over to the graph screen to look at the results there. The graph has automatically put voltage on the horizontal axis since we're in a sweep. Let's zoom in past the turn-on behavior to get a good look. As we zoom in, if you look closely, you can even see some hysteresis in the curve. That may warrant some further investigation later. We can put some cursors on the graph to examine how the board's current draw changed over the sweep. We can see that the board draws an additional 50 milliamps as it approaches brownout level before dropping back down. Let's go over to the 5 Series MSO to see how the signals on the board respond during this sweep. I've already got some of the settings configured here for viewing our frequent anomaly signal. As I press trigger on the SMU, we can see the level go high during the turn-on behavior, then the real signal appear. This signal actually behaves pretty well during a brownout. If you match up the behavior we see here with the SMU's IV curve, we'll see that the level of the signal only starts to decrease after the sweep passes that crest of the curve. One last thing I'll do is turn on the MSO's fast acquisition feature. This will allow us to view that anomaly this signal is named for. When a trace happens infrequently, it's shown in as blue, so our anomaly shows up as a blue line against the common signal. Notice it's not affected by the brownout any more than the rest of the signal. If this was a real device, this test might let us rule out a couple of options for why this anomaly is here. That's enough of brownout behavior right now. Let's change our setup for one that will let us easily see the effects of a dropout. We'll be using the I2C bus present on the demo board. We'll be powering the board with the same connections to the SMU as before. We'll start again by configuring the SMU. This time though, we'll be using the digitize current function of the 2461. We want to change the defaults for this test, so we'll go to the measure settings and set a current range of 1 amp and change the sample rate to 10,000 readings per second. Next, we're going to create a pulse train with only one pulse where we'll pulse low to simulate a dropout. We want to bias at the expected level of 5 volts. I'll set a delay of 1 second and a pulse off time of 1 second. This will buffer our low pulse of 3 volts, a level just low enough to turn the board off. The pulse width will be 1 millisecond. I know this is long enough for the board to respond. Finally, we'll set the current limits for both parts of the pulse to 900 milliamps as before. Then we'll press Generate and Trigger to start our pulse. Let's go to the graph again to see how the current of the whole board responds before looking at the I2C signal itself. We gave ourselves a pretty large buffer of 1 second on either side of the pulse. That's interesting in and of itself, but let's zoom way into where the pulse actually happened. We can again put some cursors on the screen to get some information on what happened during this time, like see the average current of 660 milliamps or a peak-to-peak current of 1.3 amps. The board actually started pushing current into the SMU when we pulsed low. Luckily, source meter SMUs can sync current just as well as they can source it. Okay, let's take a look at the oscilloscope. This time, we're going to configure the MSO to decode the I2C bus, but we're also going to use the advanced triggering capabilities of the MSO to trigger on the bus's opening declaration that only happens when the bus first starts up. You can see me setting everything up from default settings in this fast-forwarded footage. One key feature we're going to use is called Fast Frame. It will allow us to capture multiple full trigger events on the scope, then cycle through them at our leisure. As you can imagine, we'll be using this feature to look at differences in how the bus starts up from nothing and how it starts up after a dropout. Our 1 millisecond dropout is indeed enough for the I2C bus to restart. Okay, so now I'll enable the scopes trigger and then on the SMU trigger our pulse again. With the badge on the right of the screen, I can cycle between the two trigger events, or frames, that were recorded. You can see a definite difference in clock speed as a lot of the hardware was still active when the bus restarted after our simulated dropout. We might use this information in reliability testing or in building a backup power supply on the board itself.
Thanks for watching. For more information, please visit tech.com.